Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Rambus with Gary Bronner, who's going to talk today about hybrid memory. Gary, we've been following the DRAM scaling for decades now. Is it running out of steam? And if it is, what comes next?
So Ed, I agree with you. I think DRAM scaling is starting to run out of steam. I think the industry continues to keep on scaling from the 1X to the 1Y to the 1Z generation. But I think the benefit you're getting from each of those generations is getting smaller and smaller. And because of that, big servers and other memory systems need to have another kind of memory in the hierarchy in addition to what we've traditionally used before.
Why don't you draw this out for us?
All right.
So what are we looking at here?
So this triangle shows the classic memory hierarchy that is considered how you attach memory to a CPU. So at the top, we've got SRAM, which is the fastest memory and typically is now embedded on the CPU. But because it's embedded on the CPU, you can't have very much of it. And then external from the CPU, you've got the DRAM, which is typically on DIMMs. But because of the scaling challenges we just talked about, you can't get as much memory on your system as you would like to satisfy all of the demands from big data applications that are taking over the world. So what people are talking about is adding another layer of memory below that, which is between the performance of DRAM and flash, and that's what I call SCM, or storage class memory on this. So it slots in between DRAM and flash in terms of latency, cost, and density. And it's a way of attempting to add more memory when DRAM alone can't give you all of the performance that you want.
And SSD and HDD, these are typically what we've been using. It's spinning media and also the solid-state drives that are in the data centers and also in computers today, right?
Correct. That's exactly right.
So what goes together here? What are the pieces that if DRAM doesn't do enough and SRAM's way too expensive and too limited in terms of size, how do we put the pieces together?
So the first thing you need to do is understand what are the memory candidates that are out there.
What are we looking at now? This is the economics of DRAM?
That's exactly right. So this graph that I've drawn up here shows the cost per bit of DRAM on a time scale of many decades. So if you go back 30 years or more, what you see is that DRAM has dropped on a cost per bit basis roughly 35% per year for many, many years. And that was sort of traditional Moore's law scaling, where you just shrunk the lithography and the cost per bit got smaller and smaller. What you saw about 10 years ago is that because scaling was already starting to slow down a little bit, the cost per bit dropped a little bit slower than the historical norm. Instead of 35% per year, it was only 20% per year. That was still good, not as good as we had had in the past, but still quite acceptable. And what you've seen in the last year or two, since about 2016, is that the price of DRAMs has actually started to go up.
What's causing that?
So it's a combination of scaling slowing down dramatically, where it's getting harder and harder to get the DRAM chips smaller and smaller, combined with industry consolidation. So we're down to 3 major DRAM companies, Samsung, Hynix, SK Hynix, and Micron. And we're also seeing hugely increased demand for memory. Because of the big data, the huge data centers out there, everyone's trying to buy as much memory as they can, and supply is not quite up to the demand right now. So a combination of not enough scaling and not enough capacity.
And that supply is only going to get tighter, right? Because now we have even more data coming in at every level, from the edge all the way into the data center.
That's exactly right. So the demand for this advanced memory is sort of insatiable. Traditional DRAM isn't going to keep up, and that's why we need to look at other memories that can fill that gap, that have higher capacities than DRAM has, and that's sort of what we're starting to research here at Rambus.
So what's the advantage of DRAM? This is something we've grown up with in our computer systems and almost every design that we've had. What changes?
So DRAM is a great memory. It's the best memory we have that's not embedded into the CPU, and I think we're always going to need some. It's a low latency memory. It's got infinite endurance. It never wears out. It's a perfect memory, which means it has 0 errors to first order. And it's in high volume manufacturing, so there's a huge supply. So I think it's never going to go away.
But it's not perfect, right?
It's definitely not perfect, and it's got all of these problems that mean it can't supply the demand of memory that we're seeing in huge data centers these days. So the scaling limits that we've been talking about, where it's not shrinking as fast as we have seen historically in the past, isn't giving you the density that you would like. So right now, the mainstream DRAM part is an 8 gigabit part, and would like to get up to 16 gigabit, 32 gigabit, 64 gigabit, but those parts just aren't coming. We'd like the cost to keep dropping, but the costs aren't dropping as we saw. And we're also seeing that it's becoming a large part of the power in big data centers. And a memory that was non-volatile, that didn't need to be refreshed, would have huge advantages as well.
Can those challenges be solved altogether or far enough along on each one of those that it has more life and more room to grow here? Or is it just now that we've hit a wall and we have to do something else?
Well, I think we, as I said, will always have DRAM. It's going to keep shrinking slowly, but you're not going to solve these problems. So the real solution is to combine DRAM with some sort of new memory that fixes these problems.
So let's talk about the new memory types. What have we got here that has a potential for combining with DRAM?
So there are 3 or 4 major candidates people talk about as possible SCM or storage class memory. The one that over the last few years has gotten a huge amount of attention is the Intel Micron 3D Crosspoint project. I think you can buy Optane drives right now that use 3D Crosspoint, but I think Intel and Micron have been a little bit slow to deliver it in a DIMM form factor that could fit on the memory bus. So I'd say we continue to be hopeful that they'll get that technology into high volume manufacturing for memory, but we haven't seen that yet. RRAM, or resistive change RAM, is a memory that the Western digital people have said is on their roadmap as a likely follow-on to 3D NAND. And so I think that's a very promising candidate when it becomes mature and goes into high volume manufacturing. There's been a lot of discussion about STT-MRAM, or spin torque transfer MRAM, because that's got characteristics that seem like they're closest to DRAM. But since one of the things we want to get over is the cost of DRAM, STT-MRAM is not really cheaper than DRAM and fundamentally probably won't ever be cheaper than DRAM. So I view that more as a niche memory, not a replacement. And then the last one I have up here is a memory that people have started talking about, which is fast flash. It's essentially the current flash technology that everyone uses in their SSDs, and the manufacturers could make a cost-performance trade-off. A regular flash device today has latency in the hundreds of microseconds, and you could re-architect that chip to have a few microseconds latency. And that's fast enough that when combined with DRAM, it could actually mitigate a lot of the drawbacks of DRAM and give you some interesting system performance.
Do you see the DRAM actually combined with one of these in a module? How does this go together?
So the way we've been thinking about this, and we've started to actually build our own card with an FPGA memory controller that would let us combine DIMMs of DRAM and DIMMs of these new memory types. Not on the same DIMM, but on the same card.
But you also have to have very little latency between those different types of memory too, and also massive bandwidth going between them. How do you solve that?
Well, by having the DIMMs on the same card, you can have a very fast path between the new memory, whatever type of memory that is, and the DRAM. And because the DRAM is a cache, you're moving blocks of data from, let's say, whatever storage class memory you're talking about into the DRAM. And the way caches work, you only have to do those transfers relatively infrequently whenever you miss having data in your DRAM. And so that latency overhead is amortized over many, many accesses and is hidden pretty effectively.
Any other pieces that have to go into this?
Well, the other thing that you really need to find a way of doing is having a memory controller for these memories that is outside of your CPU. If you look at the way we design servers today, we use CPUs that have the memory controller embedded into the CPU. And those have management policies that are hard-coded and sort of assume latencies and other performance parameters of DRAM. So access times on the order of 100 nanoseconds. So if you want to combine a memory like DRAM with a memory, let's say, like this fast flash, which would have an access time of a few microseconds, the memory controllers currently can't handle that large of a latency range. So you really need to find a way of having a new memory controller that manages both the DRAM and the storage class memory, and that means you need a new attachment from your CPU to this memory system.
What are the options there?
Well, what we're looking at is some sort of serial attachment from the CPU to the memory system. And there are 3 candidates out there in the industry right now that are low enough latency that they could handle this kind of memory system. IBM has been pushing its Open CAPI serial interface, and it's commercially available today in their power systems. The Gen Z consortium has been pushing its serial attachment methodology. AMD and HP are big proponents of that. It's not quite ready yet, but I think over the next year we're going to see a lot of announcements about that technology, and we expect to be able to adopt that in our memory system if we want to. And there's also a consortium called CCIX, or C6, which is a little bit more focused towards accelerators than memory systems, but it could also be used with some modifications.
And so once all this is in place, how quickly do you see all this stuff starting to roll out in terms of we are going to see hybrid memory solutions in data centers as well as potentially even edge devices?
Well, we made an announcement in February of this year that Rambus is working with IBM to develop this hybrid memory system to try out a lot of these new kinds of memory. And this is a research program where we want to build this memory controller in an FPGA and have the flexibility of adding DRAM and some sort of storage class memory on this card, and then attach it to an IBM Power 9 system and run real-world applications. So we'll be able to sort of show the benefit on a system level of running different applications with these different kinds of memories and try out different kinds of caching policies on how you move data back and forth between these types of memory. So I think we'll show the potential of these kind of systems next year, and assuming that they look as good as we think they will, then we have to start discussions about how to commercialize this offering, because this will be a research platform not quite ready for production yet.
Gary Bronner, thanks for a really interesting discussion.
Thank you very much, Ed.